Remember, in the last lecture, we had seen ISI, why it was existing, and the major reason you could see that you had a band limited LTI channel, and because of that nature, when you are having a sequence of data, then we could see that that data which we was in terms of A of n was convolved with the channel coefficients, and then we got, so remember there in the last lecture we saw all the explanation, we saw this was the baseband signal of a multi-array PAM. So the PAM signal where you have one orthonormal basis, and these are the signal values that they were all real values or amplitude levels. For example, these could be the amplitude levels if we have 4 PAM or 4 array PAM, or like that if you have 16 PAM, and so on and so forth. So these symbols were multiplied with the impulse, with the train of pulses given by G, which you can say these are the orthonormal basis functions, and this was your signal that was sent. Baseband signal. Then we saw that it would be convolved with the channel, and you would get this HT minus NT. Receiver, this HT minus NT, which has passed through the channel. In chapter 8, the signal orthonormal basis was directly coming to the receiver. Here, the signal has first of all convolved with the channel. It has now become H, and then at the receiver it is convolved with the match filter. And we also saw what should be the value of the match filter, that was also discussed. And this one. So you can see the output that comes would be a train convolved with the impulse function of the match filter or the receive filter, and so because of that you can very well see that now you have this as your output. So in your output you have these symbols A of n. These symbols, you could see that they were the same symbols that were sent through the orthonormal basis or to the pulse, but now these symbols, they are being multiplied with xm minus n, which is actually the combined operation of the GT convolved with the channel, convolved with the channel filter or with the match filter. This is the combined output. So this output will be occurring with each one of those ANs, and then you can very well realize that if m is equal to n, this becomes 0 and this becomes A0. So when m is equal to n, so in that case you can see this will be x0, and an, this will become am. So for ym you actually needed am. This is just a constant which will be multiplied with am. All these terms are not needed, and that is why they call inter symbol interference, while this is your noise. All of this was discussed. So in the last lecture, in this lecture we will start from the same point, and then we also discussed in the last lecture what is a match filter. So I told you in the last lecture that yes, we know match filter is given as follows, but one wants to know what is the philosophy behind this value of the match filter, which is the, in frequency domain, it is the conjugate of the channel response, which is, h of f is the convolution of the transmit signal gt, or you can say transmit filter gt, convolve with c, which is the channel response. So you just conjugate that frequency response and e minus j2 pi ft. So first of all, we want to see its time domain, and we did all that for here, and we finally saw that in time domain this comes out to be h minus t plus t naught. When we tried to connect it with chapter 8, there we know it was tb minus t naught. So tb is just replaced by t naught. There the sampling time was, you were sampling at tb bit interval. Here you will be sampling at t naught. So this is the same. The only difference that comes is the conjugation. Previously you had no conjugation, but now you have conjugate. So question arises why this is so. Now you can very well see that if this was also, I think, also discussed in the last lecture, that if h is real, or if h is real, then there is no problem in chapter 8 and and this chapter 10. They are talking about the same concept, with the only difference is that in chapter 8 you had the signal match filter was with respect to the signal, or the correlator was with respect to the orthonormal basis. Okay? But here the match filter is not with respect to the signal, rather it is with respect to the convolution of the transmit signal with the channel, and that response is h, so it is matched to h. And so if there is no channel filter, if this h is not complex, then in that case we can very well see that our htb minus c is same as st, or you can say for this it has been transformed to htb minus c. So the match filter response of the previous chapter 8, and they both matches provided h is provided that h is real. Now, but yes, h could be real, but many times h could also be complex. Okay, and this happens when the channels are not conjugate symmetric in the frequency domain. For real signals, the main property is that their Fourier transforms are conjugate symmetric. Okay, so yes, if the channel is conjugate symmetric, okay, you could see the channel that it takes. First of all, in the book, when he starts this lecture here, you can see this very well a conjugate symmetric you can see in the I will just take 2 minutes of your time for a break. So I have one important thing. I will just try to finish that. So in this case, you can see that the channel response is conjugate symmetric, and so this means you can see both the amplitude and the phase, and you can see you have the symmetry here. Okay, because conjugate symmetric means that the positive and negative frequencies values of Fourier at the positive and negative frequencies are same in magnitude. You can see same in magnitude, but phase, the one is plus j, other is minus j. So you can see the theta phase, which is tan inverse of imaginary over real, that is मतलब के मतलब and मतलब you can say positive negative. All right, so that is why you can see that this is a conjugate symmetric channel. All right. तो यहाँ पे देखें ना किसी भी एम्पलीट्यूड में the amplitude is the same, but the phase this is negative, this is positive. So this is a property of conjugate. So if this channel is conjugate symmetric, this means that this channel will have real coefficients. All right. If you have real coefficients, then no problem. Your C is real. Conjugation with G is also, you know, a real signal. Real. The H will also be real. All right. So once H is real, so no problem. If you have conjugate symmetry, you have real channel coefficients, then you know the then you know H conjugate will give you the same H. It will exactly match with our it will exactly match with our H of chapter 8. But there are many times the channel is not conjugate symmetry. Okay, for example, if I could say in the same here, this amplitude was something different from this amplitude. All right, or in other words, the phase was not exactly, you know, same but in opposite sign. No, it was, let us say, some different value as compared to this. For this value here, let us say the value is here. In that case, it will not be conjugate symmetric. So for those cases, the channel coefficients are not real. So once they are not real, then you have to take complex. Then your channel coefficients become complex, C become complex. Hence H, which is convolution of G with C, that will also become complex. And hence your match filter will be the complex. Will be the, you know, match filter is what? It is actually H conjugate. And in that case, its conjugation will be in effect. Ari, are you understanding what I am trying to say? हाँ सलमान साहब समझ आ रहा है कुछ मैं जो बताना चाह रहा हूँ आप लोगों को?
जी सर.
Thank you. Achha, now let us go further. So we have baseband PAM, which I just showed you. Its you know, vector diagram or its constellation diagram, the same vector diagram that we saw for, you know, binary antipodal. It is just like that. You can also say it is PAM. If for binary it is, you know, binary PAM, but you can add more symbols on the same, you know, x-axis, which could represent one orthogonal basis, or you could place another orthonormal basis, but that has to be one. Similarly, we have other, you know, modulation techniques other than PAM, and that is QAM, quadrature amplitude modulation, and PSK, which is phase shift keying. I would just, this is actually, the detailed description is not in the course because we have not covered. Just I wanted to, you know, show you. There's no harm in just, you know, the knowledge. I hope is well taken from your side. So we are just wanted to show you so that you have in industry, you know, where when you have let us say you have a, you know, cable, and when you are setting your TV, let us say by yourself, many times you will find 64 what is in the settings tab, when you go, it says all right, the signals that you are getting, what is their modulation. Many times is written 32 com, 64 com, like that. So just to have an idea, so that you know you are not just totally blank when you go to the industry, especially with respect to the communication side. Just I wanted to show you. If I have some figure here, and I could actually. So yes, you can see here. Uh, this is m is equal to 4 PAM. So you have 1, 2, 3, 4 signals. All right. So you won't have at this 5 5 because you have 4. So like this 4 PAM, and they have different amplitudes. Similarly, I would like to show if you can get some figure. Yes, for PSK phase shift keying, again this is all not in the course, just for explanation. Yes, you can see here This is 4 PSK. You have 4. 2 PSK is just like, antipode link, because you have 180-degree phase shift. Here you can see that you have 90-degree phase shifts. You have 4 samples, and here you have less than 90, because you can see in one you have 2. Actually you have 1 2 3 4 8. So you have divided 360 by 8 different symbols. So you can just gauge approximately, you can say 45 degrees. So in 90 you have 2. So in every quadrant you have 2. This means that in 4 quadrants you have 8 different symbols. So this is your constellation diagram, or you can say the vector representation, the orthonormal basis. Now these could be any orthonormal basis. Okay, it's not necessary you have cos and sine. Yes, cos and sine are industrially used. We have just seen when we were studying, I think, amplitude modulation in chapter 3, that cosine and sine are the basic norms. You can carry double the signals because they are orthogonal, and then you can separate them. So here, why not use them? You have sine cos here, cos orthonormal basis for the x-axis, and sine for the y-axis. So they are orthogonal. As we saw those pulses of binary, we can also use cosines and sines, and you can have this schemes. Similarly, you can see for PAM, which is nowadays mostly used. Yes, you can see this is your PAM. This is quite complex, but still get an idea. This is m is equal to 4. You have 4. M is equal to 8. These are 8 symbols. For 16, the circle becomes bigger and bigger. You have 16 means all these symbols, not only 1 2 3 4 8, and 8 plus 4 12, but also these 4. These all symbols will be reading in 16. 16, and these are all 32. 16 plus 32 and 64. These are all 64. 64. These are all 32, and then again 32. It becomes 64. So this is a typical a typical value placements of the COM modulation. So again, the detailed mathematics is not in the course. We just have to know that the famous modulations which are used for communication. So again, now we have 2 domains. All right, and channel coefficients, they could be depending on the channel. Channel coefficients, they depend totally on the channel. Okay, and the symbols. All right, these symbols, you can see the symbol is here and the symbol is here. All right, once, because a very good way to represent cos and sine is by the famous eigen function, the famous ej omega t, because ej omega t can give you both cosine and sine representation. All right, so we can use that. The symbols could be represented along the cosine, and these symbols could be represented, these are the cosine symbols, and which we call actually the in phase, and this is called the quadrature phase. All right, the symbols could be represented based on whether they are traveling with respect to cosine or a sine. Okay, and then cosine or the sine is just, and the channel coefficients, they are another dimension. They depend on the channel response at different frequencies, so they will be finely convolved. But for now, for this PSK and COM, you are very well that you have actually 2 orthonormal bases, but for PAM you have only 1 orthonormal. So it's, if we are using sines and cosines for the passband representation, so a real axis is more than enough for PAM, but for PSK and COM you have both the axes, cosines and sines, or you have the in phase for cosine and the quadrature phase for sine. Okay, they can be well represented by the famous eigenfunction of ej omega t, and then you can apply convolution with the channel response. Channel response could be complex, it could be real, it depends on the channel, and after that convolution you can do the the demodulation and all that. First this was our binary PAM which we discussed in the last lecture. Now first of all, what I will do, I will first of all transfer my PAM to a passband PAM. Now how do we do that? We have just seen in chapter 3 that all right, you have a signal, baseband signal, you will multiply the signal with a high frequency carrier. This is your message signal or your baseband signal or your low pass signal is multiplied with the carrier, and this will give you modulated signal. So what happens when you multiply with the carrier? We all know, when we have studied in chapter 3, that whatever the uh, uh, whatever the, you know, whatever the spectrum, baseband spectrum, or the baseband Fourier of this signal, which is a baseband signal, it will be shifted at higher frequencies fc and minus fc. All right, so it will now become a passband PAM. Again, it is written vf to vf plus c. You know that what this means. This is going to plus frequency, this is going to minus frequency, and this we have learned in chapter 3. And also that cosine and sine orthogonal, they're called the in-phase and the quadrature, they become the two basis functions and all that. Now what happens for QAM and what happens for PSK? Now in QAM, we need two orthonormal bases. Without that we have no option, because it requires inherently two. So you will have both the I and the Q, I for the cosines and Q for the sines, and its signal is something like this. Now we will see also its proof here. So one train goes with the cosine, another train goes with the sine. Okay. So VCT is one train, and you can see this is the same transmit filter pulse or same orthonormal basis that were used for PAM. This is also the same. All right, but what we are doing, we are actually having two sequences. There in PAM you had just one sequence and it was only going with cosine. Here we have two sequences. One is going with cosine and the other is going with sine. And you know that they are both orthogonal when they go with cosine and sine, and they can be also separated at the receiver. All right. Now use this. What is this values of A and C? What are the values of A and S? All right. So no problem. You can, again, it is not in the course, just for your understanding and development. So you can see if you have any point, that point will have a projection onto the x-axis. If we have a COM or a PSK point, it will also have a projection onto the y-axis. The projection onto the x-axis will be actually A and C, and the projection onto the y-axis or the cosine part, or the quadrature part, will be A and S. So these are the values. Okay. Again, in PAM we had 4 values, but though all those 4 values were on the x-axis, but in COM you have values in both the orthogonal axis. We have also studied orthogonal representations. So you have both these projections, and one projection will be sent through one pulse, which will be finally modulating the cosine, and the other projections on the sine, they will be finally modulating the sine. So in pass band we have the two orthonormal functions which have been scaled with respect to their corresponding values. Now, and what is this complex number is always used when we want to represent two things. For example, electrical engineering networks or circuit networks, all that, we use this complex number because so we want to represent two things. We want to represent the amplitude. We also want to represent the phase, okay, or the phase delay or the lag or whatever. So that is why we represent. So here again, if we have two sequences, okay, and they are finally going on to two orthonormal functions, so why not use the famous complex representation? Okay, so what we do, we say that these two sequences, they can be represented, okay, as a single sequence whose real is A and C and whose imaginary is A and S. All right. So I say that my Vt is equal to the baseband signal is equal to Vct plus jVst, where Vct, which will be actually the part that will be finally going through the cosine, is actually the projections onto the cosine or the x-axis, gt and minus nt, and Vs, it will be the projections onto the the sines, and they will be Again, the same sequence is above, but we have just put a j so that we can have a compact representation for these two sequences. And this comes out, gt is common, and you have one value of an. So an is a complex number. It represents the amplitudes that are finally, transferred through the cosine part, or it also contains the values that will be transferred through the sine part. And once we have this understanding of why we are using this complex representation to represent, that is, reason is that we want to represent the two sequences with one compact, then we can very well see why our passband signal is like this. It comes to be like this because using this representation, we know what will be our passband signal. Passband signal is always, we have seen previously, it is the signal. If you could remember it previously, you had, Vt, EJT, real. When you take the real, it comes out to Vt into cosine. All right. But now your Vt is not simply Vt, a real signal. It is actually, Vt is actually sequence which is complex. It is this one. So, and you can further write this sequence as, having the real and the imaginary part. And when you will multiply with ej, then this ej will be equal to cos and sine. Okay? And then you have cos and plus j sine. So cos with this will be coming out of the real bracket. It will come out to be like this, a real signal like this. And then, but the sine with this will not come out of the real operator. But we know that the j sine for this will go with this. This will become minus negative, and your sine will come out. This was the same signal above, which is actually sent. Actually, practically, you are using this equation. Okay, you take those representations. Now those projections onto the orthogonal basis with respect to the x-axis. You modulate them with gt. You multiply with cos. Okay, and you send for one time, for n times. You will be sending, and in this way this will be formed. Similarly, this will be formed, but you can represent all of this practical signal with this compact representation. Similarly, for PSK, same, exactly same working, but your ANC and ANS, they are a bit different as compared to AN of QAM, which we saw in the constellation diagram. Here the ANs are on the same radius, and they are just phase shifted depending on whatever M QAM we have. For example, we were using 8 QAM, so they were dividing 60 degrees by 8. That is why it was coming out to be 45. So representations are basically the same, only the values change. And we have to remember that for PSK and QAM, the signal values, they are complex, but for PAM, the scaling values, the signal values, A of n's, they are real. अच्छा, यहाँ तक सबको समझ आ गया? Saman sahab, is this clear till this point?
जी sir.
Now, all right, this was up to this point, no problem. Now my signal will be sent. Remember, your signal is being sent as a passband signal. Okay, but we can write that passband signal as the baseband signal multiplied with EJ and then taking its real part, or you can directly assume that you are sending this and this signal. Both are equal. Actual signal practical is this. Okay, but theoretically you can always write it like this, no problem. Okay, whichever is easier. Here the important thing is that we are able to identify our baseband part, while here you can see that the baseband part is actually mixed with these high frequencies. This is the only difference. Okay, both this representation is also correct if you want to represent your passband signal, and this representation is also correct. Okay, both are same. Now this signal will go, now it will be convolved with the channel coefficients. All right, and convolution could be with channel coefficients that could be complex. and that they could be real. We have no problem with that. Both are acceptable. So let us say that they are convolved with CT, and CT is the the channel. But actually, what will happen? This combined this pass band signal. Uh, QT is the output, so I should say like this first of all. So this signal will be totally convolved with the CT of the pass band, okay, or this will be pass. But we can use an equal. We can say, all right, we have the channel response, we are convolving, but if we are convolving this the pass band representation with C of f, which is the pass band, what is the equivalent convolution of this baseband with the equivalent baseband of my channel? जैसे लेकिन आपका चैनल तो एफ सी पे खड़ा हुआ है या माइनस एफ सी पे खड़ा हुआ है, अगर आप ही उसको पीछे ले आए, उसको ट्रांसलेट करें कि जी वो जीरोथ फ्रिक्वेंसी पे उसकी इक्विवेलेंट रिप्रेजेंटेशन क्या थी, ठीक है, वैसे तो कन्वॉल्व हाई फ्रिक्वेंसी पे ही हो रहा है, ठीक है, बट what will happen when once this high frequency, actually अगर आप देखें क्या हो क्या रहा है, now the signal that will be received at the receiver is this thing, ठीक है, this is the received signal. Okay, again the received signal is actually the you can say the high pass version of this low. What is RT? R of t is the low pass equivalent of your Q of t. Q of t is your high pass signal, your high pass transmitted signal when it passes through the high pass channel filter or your band pass channel filter response, okay, you get an output. That output is QT, but you can write your QT as equivalent baseband, ठीक है, times the higher frequency real part. जैसे आपने उधर लिखा ना, उधर भी तो आपने यही किया था. When you were sending a signal, you said I can write my signal, sent signal was equal to the baseband equivalent times EJ real part. What again giving me the same sign, the cosine. So same representation you can use for the received signal. All right. So RT is the equivalent. All right. Now what happens to RT? Our discussion is with respect to RT, which is what? Which is the baseband equivalent signal received at the receiver. So we know what is happening, that the equivalent baseband or low pass signal, that it is actually convolved with the equivalent low pass representation of your channel plus the equivalent low pass noise, and this gives you the equivalent low pass output of your channel. It is the equivalent baseband channel response of the passband channel. So and I know VT was this thing where this AN could be complex, it could be real, that's independent. It will be convolved with CD. Again, CD could be anything. It could be complex, it could be real, and so on and so forth. Now we know, we have seen that this convolution gives us HT minus NT. That's we have seen in the last lecture. So this convolution will come out to be HT minus NT. So the received signal will be this thing, sequence HT minus NT. So you can see that instead of GT now we have HT minus NT. Alright, this is the baseband signal, understood. But just to get an idea of what actually happens at the receiver, right? Now at the receiver we have QT. QT is a high pass signal, okay? So what happens? You pass QT through with respect to cos, with respect to sine. Again, this diagram has already been studied in chapter 3 when we saw the usage of orthogonal carriers, cosine and sine, to send two signals over the same bandwidth, okay, but they will not interfere because cos and sine, they were orthogonal. The same actually is being used. This is a receiver. Same receiver that is used there can be used here, that you have the signal, and actually this is the standard implementation in all of our wireless communications from 2G, 3G, 4G. So you are actually sending your signal exactly like that. The signals are coming, and then you are multiplying this with cos, and then you are multiplying this with sine. All right. So, and then the product is passed through a low pass filter, as we have seen in chapter 3. I have also done its some of its calculation so that you can listen. So actually the high pass signal is multiplied with cos. Similarly, you can calculate the high pass signal is also multiplied with sine. So this is the high pass signal which I have definitely written here in terms of the low pass representative times cos, and then I can write this as uh, RT can be written as, actually RT can be written as RR plus JRI, its equivalent uh, you know this is baseband signal. So I know my baseband signal, it could be real, I know, but in general it could be complex. Okay, so and it could be complex because of any reasons, because the sequence was complex, acceptable, because the channel was complex, whatever the reason, that has to be covered. So it could be complex, or because of both, you had both the sequences and the channel was also complex. All right, so in general this could be a complex number. So it will be RR plus RI, and we know when we multiply this, take the real part, we will get the real part with the cosine minus the imaginary part with the sine. This we have shown previously. So you multiply with cos, cos square goes here, this comes out to be this, and cos sine, again they are orthogonal, but you can see here this comes out to be sine 4 pi ct, and this high frequency, this will be neglected, or it will be zeroed out because the low pass filter working at low frequencies. So all these FC parts, they will go zero, and because of the cosine you will get the real part. All right, real part, what is this? This is the real part, okay, of your baseband, equivalent baseband signal, okay, that is received at the receiver. Now this will be total. It will be the actual sequence, which could be complex, and then it will be convolved with H, which will be again complex. So that total thing, and then its total real is here. Similarly, if I use the sine part, I will definitely get the imaginary of the total R. All right. So R is a baseband version of the received signal. So its imaginary, the real will come from here, and its imaginary part will come with respect to the sine, because we had taken the real to be the cosine part and imaginary to be the sine part. Then what happens, that we pass this sequence, all right, through the through our match filter. So here let us say we assume that the channel coefficient, let us say they are real, all right, and we are sending any signal. We could be sending PAM, POM, or whatever. All right, so because this is actually real, so, and ANCHT, this will be your RR. So RR will be actually the real part, okay, convolved with the real channel coefficient. So this will give you the real part, and ANS, that was with the imaginary part, and again that will be convolved with the channel coefficient, which are again real. All right, so we'll get the imaginary part output, and the total receive. You can just sum these outputs, and then you can see that you are getting the complex symbols where the channel coefficients, they are real here, and so on. So, and I have told you, I have discussed why they are real, because they are conjugate symmetric amplitudes like this, and phases are negative one another, or they are conjugate symmetric. Then you can see that HT is real once, then CT is real, when CT is real, then HT is real, and then GRT is also real, and all that. But we know HT could be, it could be complex. Okay. So in that case, we will have a tough scenario. We will have A of n, which could be complex, and H of s is complex. So all of these numbers will be actually multiplied. But remember that RRT will be actually the real of the total. So this total real will come out as RRT, because all of them have been intermingled. The real, imagine. So we know RRT will be just the part that will be the real of that will come out with the cosine. And similarly, then that will be convolved with H, and also noise will also be convolved with the complex conjugate of H. So the imaginary part will come out of the sine, imaginary of the whole part. Again, it will be convolved here. And then if you sum 1 and 2, then you can see that your total complex sequence, having complex symbols, having complex term coefficients, is being convolved with the conjugate of that complex coefficient. Again, T naught minus T, we just have seen that the inverse Fourier of HFF conjugate E minus J2 pi F T naught is actually this. We are just convolving it with this. We just saw this is equal to X. With GRT with H, we have seen will give you again XT minus NT. So this will be your output. All right. So is there any question up to this point? All right. No. So let us go further. Next section is power spectrum of digitally modulated signals. So actually, you can shape the spectrum of your signals. We saw what was our digital modulated signal. It was, let us say we are talking about the baseband. So it was just actually symbols multiplied with your GT. All right. So by changing the sequences, by using different modulation schemes, along with the GT signal, you can shape your spectrum according to your industrial requirements. That is called power spectrum of digital modulated signals. So, so we have seen here that this is the representation, the baseband representation. This could be in general complex, but we can also see they are actually random, because data could be anything. What I am saying, it's totally a random process. So if the symbols that are represented, they could be representing 1, they could be representing 2, 3, whatever this, the amplitudes you have taken, they could be different. Random data could be coming out because of, let us say, speech signal or some video audio signal. And so this is random, this is deterministic signal, this is a transmit function orthogonal basis that you are using, and its train is being sent as a signal. So for different pulses, you are sending different data with respect to n time. So your V of t is now a random variable, and then you have a time domain function. This will become a a random process. So I want to find the spectrum of V of t. The power spectral density of my stochastic or random process. So we have learned in our chapter 5 that if you want to find the power spectral density, the main process that you have to find its autocorrelation, and if you take its Fourier of the autocorrelation, you will get the power spectral density. So as it could be shown here, the power spectral density of this comes out to be 1 over t times power spectral density of times the power spectral density of, and this you already we have known this thing, that this is a deterministic signal and this is a random process. So it's a random process passes through but the proof is not in the course, but just for your understanding. So we take in the Fourier domain, this we take its Fourier. So output is equal to the output spectrum is equal to the input spectrum time input of the input, which is AFN, times mod square of the PSD of GT. All right. All right. So first of all, what is the uh, PSD of the sequence? This is a PSD in the sequence, but this will be PSD will be equal to the Fourier of the autocorrelation of the sequence. All right. All right. So SAF. What is SAF? PSD of the sequence. So we have this sequence. Sorry, SAF is the power spectral density of the autocorrelation function of the sequence. So it is uh, the autocorrelation of the data sequence, and then it's Fourier. This gives me the PSD. Now, how can I find the autocorrelation function? So we have seen autocorrelation function is actually x of t into x of t plus tau. But here you can see the symbols, they are discrete. All right. So you have a of n टाइम्स ए ऑफ एम प्लस एन, ये वही है टी और टी प्लस टाउ, ठीक है ना। तो यहाँ पे टाउ जो है वो एम हो गया और टी जो है वो आपका एन है, एंड वन ऑफ देम हैज़ टू बी कॉन्जुगेटेड, तो उसने पहले वाले को कॉन्जुगेट। दिस इज ऑटो रिलेशन फॉर द डिजिटल डेटा और द डेटा सीक्वेंस with the Fourier series expansion coefficient of any arbitrary signals. That we already know that if x of t is a periodic signal, you can write them in terms of Fourier series coefficient x of n like this. Actually होता है 2j pi f naught nt, where f naught is the fundamental frequency or the fundamental harmonic. That is written in terms of 1 over t naught. And you can similarly find the Fourier series coefficients from this equation. So this will be integral of x of t integrated from 0 to time period t naught, 1 over t naught to time period, and this becomes minus. All right. So we can see the RAM, they seem to be the Fourier series coefficients of SAF. So it seems here also that if you compare this equation with this equation, so as here xn are the Fourier series coefficient of x of t, here it seems that with some little change, RAM seem to be the Fourier series coefficients of SAF. And then what is the change? The change is that periodic with a period of periodic in frequency with a period of 1 over t. So you can see here that here my t was coming out to be so here you can see that this is an f, this is an t. So t can be replaced with respect to f, all right, and nm is no problem, but t is being replaced with 1 over t naught, or you can say that 1 over t naught is being replaced with t. So here it is periodic with the t naught, while here it will be periodic with 1 over t, and you can replace n by minus f minus m. Minus m replaces n here, and you can say that f is being replaced by t. Here these were periodic representing the periodicity of with respect to t. Here the periodicity is with respect to f. For this equation of SAF, there is periodic in frequency. Periodic now it is periodic in frequency. There, they are periodic in time, but here is the periodic in frequency, and the period comes out to be 1 over t. So I can write my SAF as that t comes here, right? And minus m and all that is as the same. Same as t is replaced by f, and t is replaced 1 over t, and n is replaced by minus m. So now we can use this if x of n is given as follows. So our RA can be represented in terms of this equation also. So we will use that. 1 over time period is 1 over t. Integral will go from 0 to t. This will be SAF because now we're representing SAF. And previously you had EJ 2 pi Fn. So here over T naught, so that will become T naught will become T, and minus n, that will become equal to plus m. So minus m is replaced by plus m. Now let us assume that the symbols, these A and AM, they are mutually uncorrelated. Most of the time they are uncorrelated. So in that case, first of all, let us find the autocorrelation for m is equal to 0 when there is no delay. In that case, an into an, an to conjugate, this becomes an mod square, and then for an mod square you can use this very important principle, because sigma square, or the variance, is equal to signal minus its mean square and then expectation. I open the bracket, a square plus b square minus 2ab, and then e of this is a constant. This will come outside e. This is a deterministic function, mu square, and again this is constant, but an, its mean is mu. This becomes mu square over minus 2 mu square. This becomes minus mu square, and this is e of n square. So you can very well see that once m is 0, so you can see that the autocorrelation, which is the power, which is actually the variance plus sigma square. So here same thing, en square is sigma square plus mu square, and you can see this is different from this equation. Once that m is not 0, then in that case they are both independent, so I can write them independently, and this becomes mu 0, and this becomes mu because mean, and this also mean remains the same, and so this becomes mu mod square times mu. So this will become mu mod square. So we can see that the autocorrelation for 0 is this value, and for any other values where m is not 0, it comes out to be mu square. So your SAF, which we have driven, it is the Fourier of these coefficients. So I put the coefficients. For 0, I put this value, and for when m is not 0, this value is mu square. This comes out to be like this. So I can take sigma square, and mu, put mu square also here, because this was without m is not equal to 0, because that value is here. But now if I put mu square here, so and you have m0, so you can very well see that this will be simply 1, and you will just get Alright, this becomes mu square for all the values. It becomes sigma. This mu square goes here. And we can use this from the Fourier series analysis. We have already seen many times this thing. Train in time is actually equal to in frequency domain is a train of the exponentials. Alright, and so I can also write this as, if I replace 1 over t naught by t, this becomes t, this t goes there, this becomes 1 over t. So I replace 1 over t naught, so t by t, this t naught becomes 1 over t, this becomes 1 over t, t naught becomes 1 over t, this becomes like this. So you can very well see that alright, so this becomes like this. So for this signal, I can use this signal to represent this as a train of pulses. So my SF will become sigma square, and that this can be represented as 1 over t, this thing, into mu square. As you can see here, this mu square into the impulse train, and in this way you have driven the alright. So we will get this instead of the exponential, we have this train of impulses. So this is the spectrum of a baseband signal. Now the of your baseband sequence. Okay. Now if I want to find the total uh, spectrum of my baseband signal, which is the sequence with the GT or GTL, the formula is this. We'll just put the value of SAF from the above equation, and you will get this thing. So you can see actually this is the overall representation. You have the signal, transmit signal mod square, and here the transmit signal mod square is being multiplied with these delta functions. These are spikes, because you can apply the shifting theorem. This will only exist at the point where the argument of the impulse response is 1 or is 0. So f is equal to m over t. That is why this f becomes m over t. This will exist at values of f where f is equal to m over 1t, and they are part by 1 over t, because mt for m is equal to 1, it's 1 over t, for m is equal to 2 over t. 1 over t is frequency. These are spikes at different frequencies. And you will see if mu is 0, then this totally is 0. Okay? Mu is the mean of your data sequence. So many times if you see in the constellation diagram, for example in binary orthogonal, especially in binary antipodal, the two signals were at positive negative, so the mean was at the center, which was 0. And you can see, for example, in PSK we had those 8 symbols. They were all on a circle, so their mean was 0. Alright. Similarly, you could see in PAM you have 4 symbols, 2 over there, 2 there, or you might have 3 symbols here and here. And again, the mean of all the signals provided they have equal probability, so the mean of all of them will be 0. So if the mean of the data sequence is 0, then this factor will go out and you will only have this factor. And most of the time this is especially done so that your mean of your data sequence is 0. Hence this can be done so considered with symmetric in the complex plane relative to the origin. And this is one example. This we have seen no need for here. This was one example. This we have done now. So these are two examples, but they, they are quite simple. So you have this sequence, and you find its Fourier. Remember, this is a rectangle. Its Fourier will be sync, but you can see this is a shifted rectangle. So shift in time, it corresponds to EJ. All right, EJ minus 2 pi f t. That is why this comes out to be like this. This is sync shifted, and you can do it as spatial signal analysis. So GTF mod square, this will be your value of GTF mod square, which will come inside the spectrum. So it is mod square of your sync. Now let us see the binary sequence. So he says the binary sequence are this, where B and minus 1, they are uncorrelated. Okay, and AN sequence is actually sent. So we need to find the power spectral density of the transmitted signal. So first of all, we need to find the power spectral density of the sequence. Okay, of the sequence. So first we find the autocorrelation of the sequence. So you have this thing, and again the steps are missing as usual. So no problem. We will cover it like this. So first of all, I assume that m is equal to 0. All right. So Bn plus. So this is your actually this is your An, and this is also your An. This is An conjugate, but here we are assuming the sequences are real. Because Bn's are just +1 and -1, so they are all real. So in autocorrelation we take the conjugate, but here once they are real, the conjugation will not make any difference. Acha, just for a break. So today we will have a class till 11 o'clock. Is this because our 15 minutes were couldn't be covered in the last lectures, especially due to PEC visit. So I think, is this fine? Salman Sahab, is this fine if I take an extra 15 minutes for this class? I think Samar is not here. हाँ जी सर, वो हैं हमजा साहब बैठे हुए, सिया साहब लगता है वो भी गायब है. हाँ जी, is there the CR of C section? Who is CR of C section? अच्छा, so any person. हाँ जी, हाफिज मोहम्मद उमर, can you hear me?
Yes, sir.
अच्छा, वो आपको याद है ना, हमारे पिछले 15 मिनट रह गए थे वो पीसी विजिट वाले लेक्चर में. सो कैन आई टेक दोस 15 मिनट्स नाउ, या अगर आप मुश्किल है तो 10 मिनट ले लेते हैं, उसके फिर 5 मिनट बाद में कभी ले लेंगे, जिस तरह से आप बता दें. यानी बजाय 45 के हम 55 पे क्लास ख़त्म करें, या 11 o'clock पे ख़त्म करें.
जी सर.
कितना लें, 10 मिनट एक्स्ट्रा ले लूँ आज, या 15 मिनट ले लूँ एक्स्ट्रा? आपकी अगली क्लास कितने बजे?
सर अभी तो कोई क्लास नहीं है, आपकी मर्जी, आपने जितने लेने.
अच्छा, 11 बजे कोई क्लास नहीं है. अच्छा, वेरी गुड. तो जो हमारा 15 मिनट रह गए, मैंने कोई एक्स्ट्रा टाइम नहीं ले रहा आपका, क्योंकि हमें पता है बड़ा कंसाइज है. तो बस वो जो 15 मिनट पिछले रहते हैं वो हम पूरा कर लेंगे. ये लेक्चर थोड़ा सा बड़ा हो जाएगा, तो पिछले 15 मिनट जो हमारे वो पीसी की वजह से रह गए थे, वो हम कोशिश करते हैं. हो सकता है ज़रूरत ही ना पड़े, मगर चलें, मगर कम से कम आज के लिए हम कह देंगे कि हमारा काम हो गया. Now to understand how to take its autocorrelation, so I say take M0, which means this is also AM, this is also AM. This will be actually AM conjugate, but AM is real totally. So this will be real. So you can just write this as AM value here and AM value there. Both are same. So it was Bn plus Bn minus 1. This is also Bn plus 1. I take the product, Bn square, Bn minus square, and then because this is A plus B whole square, so A square plus B square plus 2AB. And now I apply the expectation for that autocorrelation function. E of Bn square. Bn is what? Bn is +1 or -1. And now its square value will be 1. So it will always be 1. +1, -1, it will always be 1. Alright, so mean value of 1 is 1. Mean value of 1 is always 1. Alright, but here you can see this will be expectation of these two, Bn and Bn minus 1. But we have just seen that Bn symbols, they are uncorrelated. All right, so once they are uncorrelated, I can write the joint expectation of it is actually E of Bn Bn minus 1. So joint can be written as separated of EBn into separated of EBn minus 1. But I know what is the mean of Bn. It has told me in the book that the mean is 0, uncorrelated. Each have uncorrelated mean, you can separate them, and then zero mean, the mean is 0. And variance, again you can see the variance is 1. He has written here unit variance, but you can also see similar plus 1 and minus 1, the values will be 1 and the variance will be 1. अभी तो ये हमने एक्चुअली ये हमारी वेरिएंस भी बन गई. एक्चुअली तो स्क्वायर की वैल्यू थी, मगर अगर वेरिएंस देखें तो वेरिएंस भी 1 ही के बराबर है, चूँकि मीन इसका 0 है. Right? Because we have just seen that E of square is actually equal to sigma square plus mu square. So mu square is 0. This comes to sigma square and sigma square is 1. वहाँ से ले लें, इधर से जिस तरह मैंने कहा, जिस तरह मर्जी कर लें. And here you can see mean is 0, so 0, 0, this comes out to be 0. So your autocorrelation value at 0 shift will be equal to 2. Now autocorrelation value at 1 shift. At 1 shift you have, let us say, n minus 1. तो ये an symbol होगा. जो अगला सिंबल होगा वो होगा n plus m. तो m1 वो होगा n plus 1. This n will become n plus 1. This n minus 1 will become d of n. Okay? Now if you will multiply, you can see all the symbols are different respect. This bn bn. This bn bn will become bn square. Other symbols will be bn into bn plus 1, bn minus 1 into bn minus 1, and all of them are different. So all of them are uncorrelated. You know, expectation is, you know, expression of bn minus 1 into expression of bn plus 1, and expectation of all of those are 0. So they will, all products will become 0. And again this is equal to 1, so you will just get 1. So you have found the autocorrelation function. For all other values of autocorrelation function, you know, your autocorrelation will be 0. क्योंकि अगर मैं इसको m2 कर दूंगा, you can see the symbols will be, there will be no bn now. ठीक है ना. अब ये b, उस केस में, if this is bn, this bn, this will become bn plus 2, and this will become bn plus 1. So bn plus 1, bn plus 2 is not related and anyhow with bn and bn minus 1 for m is equal to 2. Okay, so there all of their autocorrelation will be 0, and hence all their, you know, products will be 0, and hence the autocorrelation will be 0 from 2 onwards. It will only exist from with respect to m is equal to 0, with respect to m is equal to 1, and with respect to m is equal to minus 1. And the value with 1 and minus 1 will be 1. The value with 0 is 2, and you just take it, you put these values of RAM in this equation. In this equation, हाँ इसमें पुट कर लें, इधर से भी जवाब निकल आएगा, as you are just saying. Otherwise you can also do it in general equation. Yeah, this one. All right, and you can say you will get your S of f like this. तो आप इसको, वो आपके पास EJ2 by FT हो गया ना. तो यहाँ पे अगर आप देखें, so you have to take like this. So this way, RA0 will exist, and RA1 and RA minus 1 will exist. RA1 के साथ E माइनस आएगा, R माइनस 1 के साथ E प्लस आ जाएगा, ये 1 आ जाएगा, और RA0 के साथ ये सारा 0 हो जाएगा, वो 2 आ जाएगा. तो आप देख लें वही चीज़ यहाँ पे हुई, माइनस आ गया, ये प्लस आ गया, वही प्लस है मिसिंग के साथ, और फिर इन दोनों को आप कंबाइन करेंगे तो कोसाइन बन जाएगा आपके पास 2 कोसाइन. राइट, एंड दिस विल कम आउट टू बी 2 एज ये आपका जो m0 डिले के साथ. So hence SF has been found. अच्छा, इसके बाद कुछ चीज़ें यहाँ मैंने नोट्स में नहीं की, वो बुक में आसानी से समझ आ रही थी. So I can move to the book. देखिए ये आपका SF आ गया. SF को आप पुट कर दें उस फंक्शन के अंदर, अपने ओवरऑल फंक्शन के अंदर. ठीक है, और जो आपका SF आता है उसको इसमें पुट कर दें. GTF तो यहाँ आ गया था. इसमें पुट करें SAF को। GTF आपने पहले निकाला सिंक मॉड स्क्वायर वाला जो आया था, तो आपके पास पूरा SVF निकल आएगा, SVF आ गया। ठीक है, ये शो भी कर दिया कि ये SAF था आपका। SAF तो ये निकला था ना आपका 4 cos। फिर आप उसको जब मल्टीप्लाई करेंगे उसके साथ और स्केल करेंगे तो ये आपका बन जाएगा SVFF। ठीक है, पैम सीक्वेंस की +1 या -1 वैल्यू ज़ाहिर वो पैम ही होगी। अच्छा, so you can see this is your क्या कहते हैं इसको, SVFF, but this is FVF for baseband. If I want to write this for passband, so you can see what is the passband. So passband signal is the baseband signal, ठीक है, times EJT and then taking its real part। ठीक है, here we know the baseband signal is totally real। ठीक है, जैसे हमने देखा था यहाँ पे तो कोई चक्कर ही नहीं था, सारे EM सिम्बल्स आपके रियल हैं, GT भी आपका रियल, हर चीज़ रियल है। तो इसका ये हमने पहले ही देखा हुआ कि एक्चुअली ये क्या होता है, मगर इसने अपेंडिक्स में किया हुआ भी है, आप चाहें तो वहाँ से देख लें। ये 10A.3 में है शायद। तो 10A.1 तो मैंने छुड़वा दिया इसकी डेरिवेशन। ठीक है ना, अगर ये देख लें 10A.2, सो उसका रियल पार्ट लेंगे, VT रियल था तो ये VT कॉस आएगा, क्योंकि इसमें तो कोई साइन पार्ट होगा नहीं, क्योंकि आपकी सीक्वेंस सारी रियल थी पैम की। दिस इज योर UT। ठीक है, then you find it's now you want to find, because now it is difference। ठीक है, remember VT is actually a random process, so UT is also a random process now। ठीक है, so if I want to find its PSD, then you know I have to take its autocorrelation and then I have to take its Fourier। तो autocorrelation पहले ले लें इसकी। autocorrelation क्या होगा, this into this, मगर t plus tau, तो एक VT plus tau आ जाएगा, यहाँ पे cos t plus tau आ जाएगा, और फिर तो ये इन दोनों का ऑटोकोरेलेशन तो डिफाइन हो जाएगा RVT के साथ। मगर इसका क्या करेंगे हम, ठीक है, तो ये प्रोडक्ट है, प्रोडक्ट को आप लिख सकते हैं सम एंड डिफरेंस ऑफ कोसाइंस। ठीक है ना, सम ऑफ डिफरेंस ऑफ एंगल एंड सम ऑफ एंगल। तो डिफरेंस ऑफ एंगल में ये आ जाएगा, TT कट जाएगा टू, और ये आ जाएगा सम ऑफ एंगल्स के साथ। ठीक है, तो अब आप देख लें कि आपके पास ऑटोकोरेलेशन फंक्शन तो आ रहा है, मगर ये ऑटोकोरेलेशन फंक्शन जो है देखेंगे फंक्शन ऑफ टाइम है। ठीक है, तो शायद मैंने पता नहीं करवाया ही नहीं करवाया कोर्स में हमने। अब आप देखिए ना, कोर्स में जो हमारा साइज जो हमारा था ऑटो कोरिलेशन, वो सिर्फ टाउ का फंक्शन था। ठीक है ना, उसमें टी तो नहीं आ रहा था। ठीक है, हाँ जी हाफिज साहब, आपको ये बात याद आ रही है? सलमान जमील साहब अभी तक आए नहीं हैं। अच्छा जी हाफिज साहब, आपको हाफिज मोहम्मद उमर, कैन यू लिसन मी, लिसन टू मी, समझ आ रहा है आपको? हाफिज साहब, कैन यू हियर मी? कौन अवेलेबल है, किसी को जानते हैं? हाँ जी, उमैर कामरान, कैन यू हियर मी? लगता सारी क्लास ही गायब है। ऑलराइट, आई थिंक शायद most of the students have left, or I don't know. Is anyone available here which can hear me? All right. Haji Hafiz Umar, can you hear me? Like most of the students, I think they are asleep, or there's some reason they might be in some other class. But I just wanted to explain that one thing that we've actually not done, and now because of this, I think that had to be done here, because you know in our chapter 5, when we were getting the autocorrelations, okay, those autocorrelations Okay, they were functions of tau, they were not function of t here. Okay, once these autocorrelations are function of t, so first of all you have to get rid of this t. So how can you get rid of this? You take the average of these autocorrelations over time t. Okay, once you average it out, your t goes away, and then you take its Fourier to find its PSD. All right, this is the process. उसका पता नहीं क्या नाम भी था, ये चैप्टर 5 है, उसमें उसको समझाया हुआ भी था, और ये कि मैं थोड़ा उसको, आपको नाम मेरे जहन से निकल गया उसका, तो इसकी सिर्फ ये डेफिनेशन की वजह से मैं चैप्टर 5 में डाला, वरना मुझे कोई शौक नहीं था आपका काम मुश्किल बनाना. जस्ट टेल यू so that you can see. And so random processes, this was in the course, but one thing was not. Now here we saw white cyclostationary processes. Okay, so for cyclostationary, which are a function of t and tau at the same time, so if what we do, we take its average with t, and then for the average value you will see that we find its Fourier, and then we can find its PSD. This is the way we have to proceed with cyclostationary process. So here you can see that actually what we are dealing right now with these sequences. So you can see here, there again, depending on t, they are cyclostationary, they are also repetitive. So what I can do, okay, I write these product of cosines as sum of this we have done. So again, you know, they're a function of t and tau. So I take the average, I take its, you know, average value, I integrate this with respect to dt, and integrate this over the time period t. All right, so you can see that this factor, this will just come out of your integral dt because there is no t here. All right, and this factor, you can very well see that if I integrate from 0 to t, and the frequency here is 4fc, so you can see it will form multiple cycles, at least 2 cycles. So you know, 2 cycles, your cosine, its mean comes out to be 0. Means 1 is 0, 2 is definitely 0. This will totally go 0, only this will come out, and yes, this will be integral, so I will get the average value of this for one time period. This will be called RV dash. So now this is your क्या कहते हैं इसको, autocorrelation function. So autocorrelation function is this, and then this autocorrelation function, I will take its Fourier. So you know its Fourier will be just as we have seen in chapter 3. You have mt times cos, so it shifts the mt baseband to plus fc and minus fc. It will shift the rv to f minus fc. Okay. I think the proper representation, this is also right, but I think the proper representation should have been, this should be sv dash and this should be sv dash, so because we are taking the Fourier of r dash or of the average. But if you want to write like this, then there is no problem. Coming back to our part where we left off. So all right, in this way you can see we have done this. So we will go to 10.3. So 10.3 is the last section for this chapter. So I will try to cover, you know, a brief introduction, but the rest of it will be definitely covered in the next lecture, which will be last for chapter. So we will be covering chapter 10 completely from the course outline. 8 we you saw we covered just the binary portion. So 3 we will cover the total in the course outline. 10.3 we will totally covered, but we will definitely we will only one lecture left for the capacity chapter. I think chapter 11. So that we will be covered able to cover half of it. So let us go to 10.3, the last section of this chapter, signal design for band limited channel. Now we want to design the signals for these, LTI band limited channel, and how can this be done? So first we assume that there is no channel distortion. Now what this means? This means that our channel coefficient is given as follows. All right. So it only exists till W. Okay. And it is constant magnitude, and you can see the phase is conjugate symmetric, right? Now if we say zero distortion, or no distortion, then this means that its bandwidth, okay, must be greater than the bandwidth of the channel, or you can say the of the signal. The signal's bandwidth is less than the channel, so the whole bandwidth of the signal is just transferred, so the channel does not cuts it or does not distorts it. The whole signal is passed because the signal bandwidth is less than the channel bandwidth. Okay. And in amplitude multiplied by C naught, phase is just EJ 2 pi f T naught. So if I assume that T naught is 0, this means the HFF is just equal to CF into GTF, or there is no distortion, channel is passed as such. And so bandwidth of the signal, which is governed by GTF, for our case is less than the bandwidth of CF. So this means your whole signal is actually transferred or passed through SF without any distortion. So if CF is 1, let us say the CF is 1, so your total HF will be now GTF. Previously, it was GTF into CF, but with CF is equal to 1 and T naught is equal to 0, this comes out to be 1, so HF comes out GTF. GRF is the complex conjugate of the channel response into EG2 by FT. T naught is 0, HF conjugate, it is GT, and this is GTF. Again, normally GTF is 0, so come out to be HF into GTF, or GRF is equal to GTF conjugate. Now again we have this sequence. After passing through the channel, AN could be complex, H could be complex, and then we pass it through our filter. HT is equal to this thing, H is equal to H. We pass through the filter, and you will get X that we have seen, and then you sample here, so you will be getting, T is replaced by MT like this, but at any time M will be equal to N. This will be X of 0, and M and H. This will be X of 0. We have on all other symbols, M and N, M minus N, they will call ASI because YM comes out of AM. This we have already seen here previously. Now, what is ISI? That is very important thing. So ISI can be viewed in oscilloscopes. Okay, you can also see in scopes. So if you keep the sweep rate to 1 over t, where t is the symbol time or the bit interval. So you can see these are the two levels of the pan. Okay, and this is called the eye opening. It's called the eye diagram. So this is a Z distortion, the zero crossing, because different person will be crossing and they might call distortion because you don't know when it is exactly crossing, because one is mapping to the other. This is called the the noise margin, because if this is distortion, so noise could up till this value. If it is less than this value, then the signal due to noise will not, if the positive signal will not become negative signal. This is called the noise margin. This is the sensitivity to timing error, because if this is the zero crossing distortion, so this is actually defining the sensitivity. If this would be very very less, then in that case eye will be totally closed and you won't know uh, when your symbol is ending, and then you will have timing errors. So our intersymbol interference, you can see that you have one symbol, but you also have many symbols that are also coming out. So they can cause the eye to close. This is an eye diagram. This is an eye which is open. As much as it open, then this means the channel is better. As much as closed, then this means the channel has become more and more uh, distorted. So it causes the eye to close, reducing the margin for the additive noise to cause errors. So the margin is also reduced because the eye is closed. When the eye is closed, the position of the zero crossing that will also be distorted. And uh, it represents a very small margin against the additive noise. A little bit of noise will cause problems. Alright, I will end the lecture at this point. So we will be starting with this example in the next lecture. Okay. So we have covered the extra time we need to cover. If someone has any question, you can ask. I'll stop the recording.